is the swimming of a lamprey. And a lamprey is a fish, and there he is elegantly swimming. And a couple of features I want you to note right now is this nice sinusoidal wave that is going across the body. Now, I think that you will agree that it does look very elegant, but in fact, the lamprey here is a relative of the hagfish that Jean-Luc talked about. I don't think there's much slime involved, but you see it is a jawless fish, like this, and this is not the lamprey, this is the lamprey. So they're not very happy swimming most of the time, and in fact, in a lab, they're mostly just sucking onto the sides of the tank, and you have to prod them to study some kind of swimming. So, excuse me?
Two lampreys, I hope?
Yeah, two lampreys. I don't know what kind of fish that is, but in any case. So the lamprey is the most basal vertebrate, so it is a favorite model organism for neuroscientists to study the spinal cord and the neuronal signaling. And what a goal is in neuroscience is to relate a behavior to the neural signals. And so the lamprey has been studied for decades by neuroscientists, and the idea was to look at the complete coupled system of this organism where the lamprey takes some sensory input, translates that to a neuronal signal which is sent to the musculature, and of course the organism is moving within an environment, a fluid environment. And that fluid environment might, with perturbations or even during sustained swimming, sends some message to a sensory system and so on. So the kind of questions from a biological point of view that you may ask, here are just some ideas. How, in fact, does this lamprey translate a neuronal signal into a swimming mode? How do the details of the muscle mechanics or the muscle force generation affect the energetics of swimming, the swimming speed and the cost of transport? What about the body elasticity? How does the passive body mechanics translate or feed into the energetics? And so a long-term goal that we have for this kind of computational modeling is to understand neural regeneration. So I'm just going to show you this nice movie of some experiments from Jennifer Morgan's lab at Woods Hole. And what you see here you see three lamprey. This is the control. And what they did to these creatures is at some point they ablated their spinal cord in a particular place. So they injured it. And so you see this guy here is 1 week after it was injured, and the other one was, let's see.
And how big are they? You have a scale?
No, I don't have a scale bar, but these in here are probably about this long. Okay. So 1 week, and the other one, let's see, you can see the one that's 3 weeks. And here later on, the nice thing about lamprey, and it would be wonderful if this was true for humans, is that after 11 weeks post-injury, you see that it's pretty much recovered. You can watch these guys swim for a while and decide that it's almost like the control. So what would be nice, for instance, is if in a particular model where we're trying to where we're putting in the possible connectivity along the central pattern generator, the connectivity of these neurons, and we could then go into the model and tweak it by changing the connectivity and so on, and then couple that with the muscle mechanics, with the fluid mechanics, and relate that to the observed swimming patterns. So that is a long-term goal, but I'll tell you where we are right now. So again, the swimming of not just the lamprey, but the motion of all organisms in an environment is a closed loop system like this. And so what I'll first tell you about is a simpler way, a simpler model where at first we are taking away the sensory input, and we're looking at a non-closed loop system. So we're going to first take the neural signal as an input to the model, but we're going to fully couple the muscle mechanics and fluid dynamics. So what is wonderful about a lamprey is that, well, I think it's more wonderful about the experimentalists. They were able to excise the spinal cord. This preparation goes back at least 20 years here, and Avis Cohen, our collaborator, was one of the pioneers in this. Does it normally just come back? There. Where you could take away all the tissue and the muscles and so on and put the spinal cord in a dish, and you put in the proper chemicals in the bath, put electrodes in, and this guy for a while will still swim in quotation marks. It's called fictive swimming. You can still you can still measure the wave of electrical propagation down the spinal cord. And so what I want you to look at here is that these are recordings from the 7th segment on the right side and the 19th segment on the right side. So you see that there's a wave propagating from the 7th segment to the 19th. And then over here, you see the left 7th segment and the left 19th segment. And what you should see from here is that the corresponding segments on the left and right side are firing in antiphase. Okay, so this is the signal that is going down the left and right side of the lamprey. And here, well, I'm just showing you the same thing. Here's a schematic. So one thing that I believe Dan Goldman talked about is that for most fish, if you look at the wave of electrical propagation down the body versus the mechanical wave, the sinusoidal shake, there is a phase lag. And one could ask, what is the function of that phase lag and how does it occur? So for instance, in a fish or a lamprey, here it is, head to tail. If you put an electrode in this segment over here, when it's receiving that signal and you look at the length of that segment, the length, when the electrical signal is on, the length is decreasing, so you're getting contraction, which is what you would expect. But as you go down down towards the tail, here, when you see that this segment is contracting, even though it's not receiving an electrical signal at that moment. So there is a phase lag. Here, finally, when that muscle segment receives a signal, it's actually lengthening. So here, this is sometimes called a lengthening contraction. And so you might want to ask what the function of that is, and is it observed in all fish, and in a model, do we perhaps in a mechanical / fluids model, do we have to include sensory feedback to see that kind of delay? So let's see. So how does, I told you we're going to take the wave of electrical activation as an input to the system. And how does that then translate to communicate to the skeletal muscle? So just quickly, when that muscle segment receives this signal, that burst that I showed you there, what happens is there's a cascade of calcium dynamics. The free calcium is then is taken up by the thick filaments, and that contributes to the shortening of the muscle or force generation, and then when that signal is taken away, the thick filaments would release the bound calcium and so on. So what we've done is to take in that wave of the activation signal and we want to translate that to force generation. So I'm not going to go over any details, but we have a detailed mass kinetic model where we're tracking in each muscle segment, we're tracking calcium dynamics, and we're keeping track of how much bound calcium there is in a particular muscle segment. So just suffice it to say that here we're going to have an on and off, a signal, whether the stimulus is on or off, that is feeding into this mass action kinetic equation for bound calcium. So I'm just putting this slide up here to show that the activation signal is driving calcium mechanics in a muscle segment, and from that that is going to feed into a force generation model. So what I want you to see from this slide here is that we're going to, on a particular muscle segment, we're going to figure out what a contractile force is depending upon the amount of bound calcium, and it might be length and velocity dependent. Okay, so this is a hill-type muscle model and so forth. But here now we want to stitch it all together to a mechanical model of a lamprey. And so I want you to look at this schematic. So far I've told you about the calcium mechanics that's getting information from an activation signal, and here is the actual mechanical model. So it's a complicated, simple model. What do I mean here? We are building this lamprey out of 3 filaments. On the left side and the right side, or the top and the bottom here, we're going to have, here's an individual muscle segment. And that individual muscle segment is going to support its calcium model here that I described earlier. And it's also going to have some passive Hookean elasticity. Okay, so we're stitching this together by a series of nodes and linkages, and the links are either Hookean springs or nonlinear springs like collagen. So we're going to take this structure, which is informed by the calcium mechanics, which itself is informed by the electrical activation, and this is going to generate forces, mechanical forces on a surrounding fluid. So the idea is, or the question is, can we do this? Can we build a computational lamprey that takes in a wave of action potential, generates realistic muscle forces, and its elastic properties are like real lamprey, and can it swim? And the methodology that we've used is an immersed boundary framework where we couple a full Navier-Stokes fluid with an immersed boundary that supports forces. So many people have talked about that already, and I will not go through any details. But here we go. Obviously the answer is yes, that we can do this. And so what do you see here? So this is you see this swimming, you see the nice sinusoidal wave, and you see the nice vortex structure that it is shedding. So what I want to point out is what is input into this model and what is coming out of the model. So what we do input is the fluid viscosity, the passive elastic properties of the body, the maximal muscle force that could be exerted on a segment. What is not coming out of what is coming out of the calculations that's not put in is the waveform, neither the amplitude, the wavelength, or the swimming speed. So this is a fully coupled system where what's coming out is the body kinematics emerges from this, as does the swimming speed. So to just show you what range of Reynolds number we're working in, if we use the body length scale and the swimming speed, that we get a Reynolds number close to 8,000. But if you just look at if you take the length scale to be the width of the body and the amplitude, the velocity of the tail going up and down, it's much smaller. And here in particular, even without sensory feedback, we do see that we do get a phase lag, that the wave speed, the actual mechanical wave, is moving 88% slower than the activation wave. So now we can ask a bunch of questions here. So let me just show you for the numerical methods enthusiasts in the audience. This is using an adaptive mesh refinement, very important here, to capture the boundary layer and the vortex shedding. And so what we're being careful about is that the background grid here is refined near the lamprey and near regions of high vorticity. And what we've done is computed this with lots of resolution and much less resolution. And in fact, one gets the same body kinematics even if you don't resolve the vortex wake all that much. So for people who really love vortex wakes and think that all of the information is encoded in the vortex wake, this is not such good news, but I don't mind it. Okay, so now we play this game here. Let's see what happens for a different kind of swimmer, where we take the muscles and make them twice as strong, but at the same time make the body twice as stiff. So here we've done that, and you can watch this lamprey swim, and you don't remember exactly what happened in the previous one, but we could do the same thing in the opposite direction. I'll compare in a minute. So here, this is a much floppier swimmer. So what we've changed here were the passive elastic strengths on all of those linkages that made up the body. So they all swim, but let's see what happens when we put this all together in one movie. So stiffest, moderate, most flexible. You see the red one gets out of the gate fastest. But after a while, let's see, I'll show this to you one more time. After a bit, you can see that the distance between their noses are pretty much the same. So while the stiffest one accelerates more quickly, after a while they tend to swim at the same speed. Question?
Are these simulated all together?
No. Those are the 3 simulations that I showed before, but we put them in one movie. So in fact, I'm just showing you movies here, but we could calculate the energetics of the swimming in all of these. So here's what I want you to look at. So this is the swimming speed of the center of mass of each of these cases, and the green one is the stiffest. So you can see it accelerated quickly, but then had this pretty much steady swimming speed. The most flexible one certainly took a lot more time to get up to the swimming speed, but after a while they're pretty much going at the same speed. However, when we measure the energetics and we look at the amount of work, we see that the fastest swimmer that accelerated, the stiffer, stronger swimmer, used much more energy or had to perform much more work to get there than the flexible one. So we may think that that stiffer-bodied swimmers are good when you have to get the heck out of the way if something is trying to eat you. But a more flexible swimmer, if they don't have to run out of the way so fast, they would require less energy. Okay, so here, what I've shown you here is results of this simple yet complicated model, because at every one of those, at every segment, we're solving calcium mechanics, we're solving calcium dynamic equations, we're coupling that to muscle models and so forth, and we're stitching it all together through this mechanical model that's coupled to a fluid. And so this is a 2D model, and we wanted to see if this is a good reflection of the real lamprey or eels. And at the same time, we were working with Megan Leftwich and Lex Smits, who had a lab in Princeton where they were building a robotic lamprey. And so at times, so we compare the vortex shedding of, this is from George Lauder's lab, where this is the wake generated by an eel, this is the computational lamprey, and this is the robotic lamprey. So one thing that we also want to look at is the role of flexibility, and we talked about that a little bit. But a lot of people, including some of you in the audience, have looked at the role of flexibility in swimming, and the question comes up, does resonance play a role? Can you find the natural frequency where you oscillate this elastic structure, and if you swim at that natural frequency, do you get a boost in swimming speed? And so with the robotic lamprey, they did in fact put a flexible tail at the end of it, figured out by taking this flexible tail and waving it, figured out what the elastic modulus of the tail was, and then swam it at that frequency, and in fact there was a real boost in swimming speed. When I say swam it at that frequency, the servo motors were set to propagate a wave at that speed. We did the same thing with our computational lamprey, where we took it and waved it and decided what its natural frequency was. And in fact, we do see that we get a resonance peak here, let's see, right over here, at a frequency of 1/2. And when we propagated the activation at a frequency of 0.5 hertz, we actually did get a peak in the, where is it? Here. Here, we did get a peak in the body lengths per second. So what's been very nice about this project is having our computational lamprey grow up at the same time as our robotic lamprey, and try to do similar experiments on each one, understanding what the elasticity was and so on. So yes, there is some. There's not one resonant frequency for many of these structures, but there is something that you can get out of it. So in the time that I have left, I want to show you a couple of things. I want to show you how we've been closing the loop and including some sensory feedback, and then I'll show you some interesting interactions. So like I said, what we were doing beforehand is taking in the signal of electrical activity. So what really does this look like here? Now, a very comprehensive model would be solving Hodgkin-Huxley type equations at each segment. But this, one needs to step back somehow and see if you could tease out the elements of what's happening without putting in the entire complexity. So that's the approach that we're first taking. When you look at this, the electrical propagation here, what are the two features that are important that you can that you could take away from here? There's a wave speed down each side of the body of the signal, and it's firing in antiphase. So if you stand back from this, we are not in any way trying to resolve these spikes. But the information that we're really getting from here is the speed of this electrical signal and the phase difference. So people previously have used simple coupled oscillator models, phase models, and this is our starting point. So what we'd like to have is that on each muscle segment, the signal is going to come from a phase oscillator. So we'll attach some clock to it. We'll attach some angle theta. And we could go from an angle theta to this signal by looking at sine of theta, putting in a cutoff, and when it's above that certain value, we'll say that that muscle signal is on, otherwise it's off. And we could look at the coupled system of these clocks or phase angles along where here one of these indices is going along the length of the body, and the other index is going across. So we have intersegmental coupling and intrasegmental coupling. And so without this last term here, what we could tune this coupled oscillator model to have a given wave speed along the body. So instead now what we're going to do is to include some type of sensory feedback. And it is known for lamprey, for instance, that there are these edge cells that do live in the spinal cord that are mechanosensory. So they could sense stretch, for instance. But it is not completely understood as to how they change the pattern of neural signaling. So my collaborator Eric Teitel, who is a biologist at Tufts, he is using a similar preparation I showed you before, where you could somehow dissolve or take away the firing along the central pattern generator, but keep the edge cells alive, and could measure the firing or the input of these edge cells and see how they respond to mechanical bending of that spinal cord in the dish. So it's unclear at the moment, this is still not known, as to how the edge cells fire. Does it depend on curvature when you're bending this spinal cord, or does it depend on the rate of change of curvature? Even if we know that when we curve it, the edge cell fires, we don't know yet how that is altering the central pattern generator. So what we're assuming is that there's going to be some sensory feedback that's going to depend on the curvature of the lamprey spinal cord. And so what this functional form is not known. There's some experiments trying to get at that, but that's the beauty of mathematical modeling. We could say, well, imagine this or imagine that, and see then, putting it back into our model to see how that changes the swimming mechanics. So I'll show you results of one assumption here. Let's imagine that if you take your lamprey and you're looking at the phase oscillators at each segment, if you curve it to one side, if you curve it one way or the other, it's going to excite the CPG on one side, and on the other side it's going to inhibit it. Okay? That's a reasonable assumption, as reasonable as anything else. So we did that, and we put it into the model. And here, what I'm showing you is here's B. Here's the swimmer with no proprioception. It doesn't know what its curvature is. It doesn't care. And here, A and C are two other swimmers that have this kind of plus-minus proprioception, where the gain is positive in one and negative in the other. And you see that they swim more slowly. So why is that? And in fact, so here the gain coefficient of 0 would mean no sensory feedback. And here, positive, negative gain. I'm not sure what that blip is, but you see it swims more slowly. However, I don't have this slide here, but we could also measure the cost of transport. And in fact, the cost of transport goes down monotonically with the gain. So I can't remember which side is which but here what I'm saying is we measure the curvature. On one side, that excites the CPG, on the other side it inhibits it. What I'm telling you here is that when we include proprioception, doesn't matter, both things swim more slowly. But it's much cheaper for the organism to swim with one sign of gain than the other. So let me just show you what we learned here. And we found this, we didn't expect this. So here is the control, the middle row is the control, and this is activation. So red, right side, blue, left side. So here the muscle signal, the signal is on, off, on, off. What you see here is that the frequency during time 7 to 9, so this is negative gain, positive gain. The frequency of these signals didn't change, but the duty cycle changed. The amount of time that this blue segment here was receiving a signal is shorter here than up here. So the duty cycle changed, but what am I plotting here? I'm plotting the force generation in each segment. So this is a particular segment, I should have said. So let's look here. For this negative gain, the duty cycle of the segment is longer. So that muscle segment, when it's feeling that electrical burst, it's longer. So, but look what else is happening. There is, if we look at the force generation, there's a segment of time where there's non-zero force generation on the right and left side. So this is co-contraction. So that means that the muscle segment on this side and this side, they're both contracting at the same time. That's a lot of waste of energy. So here for negative gain, we see that we're getting a lot of co-contraction, and this is causing that swimmer to go more slowly. If we though look at positive gain, what's happening is here the duty cycle here is decreased, so each segment is getting a signal for a shorter amount of time, which makes things go more slowly in some sense, but look at the co-contraction here. So again, this is what I told you. This here, the cost of transport is low. And here, if you look at the force generation in the right and left segment, the amount of time they're both on is very small. So this is a much more efficient swimmer. Now, of course, we have no idea whether this is what edge cells are doing. I will tell you that we have another model where we believe that the curvature either excites both sides at the same time or inhibits both. And what we see there is that the only thing that changes is the frequency of the wave. So yes, there must be much more complicated functional forms, and in fact, just when we're getting ready to put this together, it is looking like from Eric's experiments that the edge cells are responding more towards the rate of change of curvature and not the exact curvature. So that's something that we're going to look into. Okay, so finally, I just want to show you some things that we're thinking about, which are just movies, so you don't have to think too much. So the future work, we're going to be, like I said, looking at different forms of proprioception, but just for fun, and let me go through this quickly. We've been looking at some heaving panels, but I'm going to skip that. For fun, we've been looking at interaction of swimmers. So we saw a lovely talk about micro swimmers the other day, where one was studying alignment. Do micro swimmers want to be aligned, or do they not just their direction but their body shape? So here's a movie of two lamprey who are in opposite phase. So these have no sensory feedback. These are just have waves going in. So do they want to stay as mirror images of each other? And these are calculations that we did only a few weeks ago, so I don't have it run any longer. But it looks like they're not it looks like they're veering apart, doesn't it? Here's two identically actuated swimmers pretty close together. They are feeling the vortices that each other are shedding. And in fact, they don't want to stay parallel to each other. Now, I can't tell, so this is not reached steady state. There are strong starting vortices, so I don't know what the answer is here. And I want to say thank you and put this with two identical swimmers, one behind the other. I know that this is a setup dear to some people's hearts here, but the surprising thing is in here for me is that the guy in the back says, I really don't want to swim in his wake. So there you go, lots of interesting things to study. Thank you.
Questions for this? I have a question. I remember reading a paper one day about someone in biology asking the question, what's the smallest fish that can swim? And I'm wondering if you could use your simulations to complete model the coupling between the muscles and the...
It's a good question. Laura
Whether
or
there's a
Mimi
limit
should know the answer to that.
Well, larval fish are like a millimeter, so they don't make them smaller than that, so I don't know.
Reynolds
she could
number
try
is
it.
about 5 to 10, depending on how you calculate it.
Any other comments or questions?
If you strip away the kind of neuronal component, is it known what the kind of, optimal kinematics are for swimming, and how close is this to that?
I don't know how to measure optimal.
For maybe fixed mechanical work on the fluid?
Yeah, no, I don't know. Thank you.
Okay, let's thank Lisa once more.